Thanks, Barry. Thank you for your comment and for listening. One thing I always think about when I see Bill's presentation and the work we did 20 years ago now, is that it had not been for all the dredging of St. Clair, all of our cottages, you have 2 feet higher water level. That would be the natural level. So it's really amazing to think about that. The natural level on our lakes, our lake is 2 feet higher than the nearest right edge. At any point in time, it is 2 feet higher. Okay, so but I'm going to talk about something a little bit different. It's some lake hollow predictions we've been working on, and I also focus on or take a look at the environment. And so a little bit on background on predicting future lake levels, whether we can predict future lake levels. Talk a little bit about the Environment Canada study. That was very alarming. Some of the predictions that came out of it last summer. Bill's giving me a good introduction on that. And then U.S. federal agencies are doing a similar study to Environment Canada. I'll touch on that briefly. That should be out the next year or two. And then an update on our predictions, which is a different approach, but seems to be working, at least for short-term forecasts. So, Environment Canada used a very complex numerical modeling approach, which takes models of the entire planet and then downscales it to the Great Lakes, and it had attempts to take those changes in evaporation and precipitation and predict changes in lake levels out of the 50 years. So I'll talk a little bit more about that. The Corps of Engineers, NOAA, USGS are working on a similar study, as I mentioned. It's more detailed, a lot more dollars going into it, and it'll be a lot more current when it comes out. And it's also going to predict future waves and storm surge as well, both for the Canadian side and the U.S. side, what they're focusing their testing of it on the U.S. side. I'd really like to get something to fund in our government to fund sort of taking that view and applying it to the Canadian side. Could be much more comprehensive than where Canada's. The problem with these approaches, they both rely on the climate models, the GCs, the global climate models, the GCMs. And the GCMs don't really account for a lot of cyclical factors in climate that the one exists, whether it's El Nino, La Nina, you hear a lot about that in the news. That's a quasi-cyclical oscillation. There's an oscillation in the Atlantic called the North Atlantic Oscillation. So there are different climate oscillations that aren't really help us, and particularly some of the solar-driven ones are not. And I can see why the solar-driven ones are, because it really doesn't have an impact on the oceans. But it seems to have a big impact on the Great Lakes and the Atlantic. The solar-driven cycles are not really, or they're not included in the GCMs. But I think that the Great Lakes are important. So the approach that we developed is really a simple approach to say, we all know that the lakes sort of follow some sort of cyclical patterns. And are those cyclical patterns driven by solar cycles or by other cycles such as the North Atlantic Oscillation, which are not really that well understood. And we found that you can use that cyclic behavior to forecast. And I'm going to show you how we've proved that we can do that. But back to the Environment Canada study. So, as I said, complex numerical modeling approach, it's models the entire climate of the planet and then downscaling that to the Great Lakes. This is the grid resolution of the Great Lakes. So if you can see, they've only got maybe 5 or 10 points across Lake Superior. So it's not a very fine resolution, even at this regional scale. I was trying to out here and I was thinking, this talk's probably too technical. So I'm going to try to simplify it as much as I can. You can ask questions quick. So what they do is they take the meteorological output from these climate models, so winds, temperatures, pressure, and precipitation, and then they run that through runoff models to give the amount of water that gets into the lakes. And then they have lake models where they look at the balance between rain that falls on the lake and the evaporation. And those are the 3 main factors that go into the water levels of each lake. And then obviously there's flows when you between the lakes that I can share too with as a model. So as I said, these models don't consider the solar cycles, and they only have a limited approximation of other climate drivers, and so is the which does affect our climate here in the Great Lakes Basin and the North Atlantic Oscillation. So that limits their ability to predict the future in a time series sense. So they can't say, and I'll show you why is this is playing true in their results. They can't say what the water levels are going to be for the next 10 years. They can give you some indication of the probabilities of what might happen, but they're not realistic outcounting time because they don't consider these factors. You saw the solar cycles and the other drivers of a cyclical patterns. So whenever you develop a numerical model, the standard practice is you calibrate it first to make sure that it matches the data you have of what you're trying to detect, in this case water levels, and then you validate it to say, okay, I look at a different period of time, is my model able to predict what happens? In climate modeling, because it's so complex, I don't think they haven't got there yet, but they do something called bias correction, which means that they see how their predictions compare to actual measurements, and then it's an effective calibration and try to tweak it to bring it into to match the predictions. Like I show you some of what environment atlas does, and the degree of uncertainty associated with what they're doing. So let me go to the last thing. So this is from the environment atlas report, and what they're showing here. So what they did is they took 1961 to 2000. So that's their sort of their test period. And they take, this is just for precipitation. So it's total precipitation in a year over the Michigan-Huron basin. And these are the different models they use. So this is the different data set I think than Bill showed. It's been out of their report, and I think they've slimmed down the number of models they use. Each of these different colors is a different climate model. So there are probably 20 or 30 is the climate models that are run around the world by different organizations and produce different predictions. So each of these different colors is a different prediction with the precipitation over the Michigan-Huron in an average, like the average year of that full 40-year period, which is interesting that they take an average approach on their comparisons. We know that the years vary a lot from year to year. The average doesn't really read a lot, but that's what they're basing their approach on. So this is 50 millimeters. So this is a factor of 2 in precipitation. The black line is the actual measured average precipitation over a basin by NOAA over that period of time. So that's what they're trying to match in the east. You can see that these models are a factor of 2 out on precipitation in any given wealth. Some are close, but some are a long way off. None are close all the way through. So then this is without the bias correction. Then they do their bias correction to try to bring their models for precipitation, and I'll show you evaporation runoff next, into that black line. They never in their report show how well they did on the bias correction. There's one graph for Lake Superior for one, I think it's for precipitation, but they never show how well they did on the bias correction. And by doing this sort of amalgamation into an average month, they can't predict what the water level is, what the true water level will be 5 years from now or 10 years from now. They can predict a probability of the range you might see over 50 years. But it's not like they can't predict any time. But they predict purely probabilities. So this is runoff, black line here, and here's all the various climate models before they're corrected to try to pull them into the black line. Again, more than a factor of 2 on runoff in many places. And this is evaporation, which is a terrible act. And in fact, it's the weakness of all climate models on the Great Lakes. The other study, the U.S. study I mentioned by the Corps of Engineers, were involved in that study, and they have a big problem now in getting evaporation right. So the black line again is what the history tells us about evaporation on the lakes in an average year. And interestingly, evaporation is lowest in the summer, and Fingal and highest. And the reason for that is because the water temperature and the air temperature in the summer are close, and generally winds are less. So it's really winds, the difference between water temperature and air temperature that creates evaporation. The models are getting it completely wrong. So they've not shown how they bias correct most or how well they did in bias correcting, but I think effectively they stepped up reflecting the exact opposite the models are giving to get it right. So just to summarize, they never show their bias corrections, except for one statistical example for Lake Superior precipitation. They can't capture any simple patterns just by the approach that they use. That's not necessarily wrong. It just means we have to interpret what they give us in predictions with caution and with awareness of what it really means. The other thing is, as I said, here they've used, I think, maybe 10 different models. They should have done a screening process. We were doing a similar study to this from the U.S. Navy on the East Coast, the Chesapeake Bay, as a pilot study to look at vulnerability of all the naval bases around the world, U.S. Navy bases around the world. You need to select the appropriate climate model that works for the region, and they didn't do that screening process. They did throw out a few, but I think they should have thrown out several more. And so then they treat those other predictions, they treat all the models as possible predictions, when in some of those models really don't work well on the freeways. They should have been thrown out. They threw out a few, but they should have thrown out one. The other problem with the environment kind of study is it relied on model results of what's called CF5s, which is a couple of lolly in their comparison question with which comes under the accuracy of their estimate about climate change. So they see that 5 was for the 5th assessment report, which came out in 2014. That's been completely outdated now by the CMAC 6 results that were available in 2020. And so it's 10 years out of date of models, and it's a whole new set of models and predictions. And this is a problem in environment Canada studies for, we work a lot with government and there are applying colonization, but it just takes so long for them to get this information out. We knew that they finished their work 2 or 3 years ago, and it did as until last week we find this out. Anyway, it's out of date. And then looking at their predictions, first of all, we all touched on this a little bit. Of our RCP 815, I think it's a 4.6 degree by 2100 increase. Something like that. You call it business as usual. What we know we're not pointing to business as usual with all the electric vehicles coming online, conversion of coal to gas plants, wind power, et cetera, who we're not going 8.5. Now, you will find some people would say there are some uncertainties and we should still keep this worst case scenario as a consideration. And I think most people will agree it's not likely in future. Okay, so this is just, they'll show this similar slide. I think it's a fewer number of models here, but this is the past lake levels, annual means, and these are the future means predicted by all those different 10 or 12 different models in the future. And we do see that rising trend, and they'll point it out. But you can just see my point here that you can't use this to look at what water levels will be in 5 years, 10 years, or 20 years. Because just look at, this is 2010. They started their water lake in 2010. So for 2010 to 2020, we should have been sitting up around on an average 177. We're not at 177 that well, we're well below 177. So it's a probabilistic prediction. So it gives you some idea of what might happen. But I don't think you could trust walls out here or down here. We don't know how good those models are and which model do we trust. There's so many different models in there. So there's a lot of uncertainty around them for all the reasons I'm explaining. Really important disclaimer. And I think maybe that's what led to the retraction, hardly of the GDA article on the Environment Canada study. So it's, you read the reading. It's basically saying, you're extremely cautious with interpreting, and particularly the ones that are at the limits of the range. In a sense that don't panic. There's a lot of uncertainty around this, and the uncertainty hasn't been very well, I would say, quantified or communicative. But this is an important paragraph from that study. Okay, I mentioned the U.S. study, much more comprehensive study, a lot more dollars involved, and it should be available. And they are using CNIP 6, which is the most recent. Our global climate models and the zone climate models. It should be out, I think, next year. Now, I was talking about it yesterday, they're having some problems on their timeline because of some of the issues with evaporation. But this is the timeline schedule. So, let's see, Lake Michigan-Huron to be available. I think that would be next. It's supposed to be available next fall, I guess that is. But we'll see then there. Right, understood. Okay, so that long story, when we did the St. Clair River study in 2005, I'm not going to point out why we had this, but we had to develop an understanding of the fluctuation in the lake levels. And so we took what's called a harmonic analysis. So those who are familiar with music, there's the harmonics in music, and you can sort of study the sound, the wave, and detect the sound with the different periods of the sound wave and make up the sound. So it's a similar approach to looking at lake levels, because the lake over a series of waves over the last 2 or 3 years midday or 4, 10, 12 years. So we did our initial development of some approach and predictions in 2005. So then we predicted levels of Lake Erie for, like 50 years. So we can see how well did we do with that. And then since we updated this in 2019 with some extra funding, and Mary provided us. This was funded out of the work that Mary had when she was at GBA. This was funded by Greg's Unfortunate Foundation. And so we updated our method in 2019 and see what we came up with. I'm not going to go into this, but this is just an example of a harmonic study you get when we study the different the data set we have for the last 100. We go back to 1860, and then there is actually data back to 1913, so all it's trying to be a little over 2 years. So when we take all those harmonics, we can predict. So the orange here is predicted, and the dots are measured. This is still Lake Erie from 1900 and 1950. So we get the general trends of ups and downs, well, so you don't get exact peaks and lows and V's, but we get the trend. Now this is a calibrated model, so you would hope that it would match it, because that's what it's trying to do, is use the cyclical patterns to match GE. So we match the data well. But then what we do is we validate the compass, which the climate models don't do. We say, okay, with our model, we've calibrated it against existing data. How well can you do in predicting the future? Quality prediction of the future. So this is Lake Erie. We basically had our model calibrated up to just around mid-2000 or 2005. The yellow dots are our predictions, and the black line is what actually happened. We predicted pretty much 10 years of water levels somewhere here. We didn't see any extreme jumps or falls, but in itself, that shows that the method is working, because our method does have cycles that go way on and way down. But for this period, it was remained relatively stable. We began to get out of sync with reality about 10 years out. Okay, so that is 2019, we updated things, and the blue dots now are the updated model. The red line is the predictions, the updated predictions. The black line was our old predictions, and here's where we went out of sort of lost. We were not synchronized with the reality. So we've updated our method now. And then the blue here are our predictions on Lake Erie since we updated it. So no changes. This is just a complete verification of the method. So we're catching that down when falls very well on this theory. So then we could take that method, updated method, and say, okay, well, what's going to happen in the future? So we're coming down now. We're going to remain steady or average for the next 5, 10 years, and then predicted to drop a lot in the beginning of 2030 to very, very low. We would see lows. Whether that on these, I would say I wouldn't trust. 10 years out, I trust in the approach because it's proven, and we've done it and shown that it works. So Michigan-Huron, it's more difficult because we've got more stuff playing on. Lake Erie is pretty simple because you got the water coming in, and it goes over the falls, and then there's a little bit of influence from coming to the St. Clair River, but the falls is always the falls. Nothing changes there. There's no regulation. But Michigan-Huron is a little more challenging because of the regulation and the balancing that Bill talked about at the St. and the ice jams and the erosion. So it's a little more difficult to predict because we don't consider all those details that I'm at. Okay, so just to show you a little bit about what's behind this prediction method. So this is the data from Michigan-Huron and Erie, and this is the underlying longest cycle in found, which is one of this year. So that was actually not just based on this data, but based on 3,000 years of data from what's called paleo data beach ridges on the bottom of Lake Michigan. So that cycle is identified. You can see, so it goes through the data first walk, natural measurements. Then we add in a 30-year cycle. Everybody sort of knows that to be the Great Lakes, there is sort of roughly a 30-year cycle between, the 50s and highs in the 50s, highs in the lakes out of these, highs in most recent what you see. You add in that 30-year cycle, and you see that we begin to pull into the actual red measurements better. And then we add in the 11-year cycle, which incidentally, this is probably the only cycle I would say that is fully accepted within the scientific community as a reliable cycle, solar cycle. So it's a solar cycle. Any publication you'll read, all the readers of the 11-year cycle, and it's not that variable. It's between like 10 years and 12 years. So it's a very well documented, accepted cycle. Anyway, you add that in, and we get even closer on the water. And then we add in shorter periods like the North Atlantic Oscillation and the El Nino and Nino, and we pull right into the data. Another test we did against this method for Michigan-Huron was we used mostly the data after 1865. So, but there is sporadic data, which is the blue dots that we're measuring back to 1819. So we look backwards. How do we do if we sort of backward predict the wall? You know what we do with all those highs and lows when we backward predict. Now, we've got the 160-year cycle in there. And so that helped us do this. But all the other cycles, we derive from all the data on this side. So it's almost a blind prediction, and it is really low. So what are the future water levels supposed? Sure, this is then the same thing. This is saying, okay, well, we take our method, and then we compare it to the which our hard predictions are in orange, and the dots are the measured. If we add all those different harmonics in, we predict the water levels really well. And again, you're expecting, because we're sort of telling here. So we predict the future, or sorry, predict the last 50 years really well. So then the second thing is the huge. So it was 2019 when we set our wall of 180. And these are our predictions. So we got the drop, but we're out in year. So we predicted a year too late. Maybe 2 years, but maybe 2 years too late, depending on what they measure that. But we've got that drop. This is actually what's happening. The orange. Sorry, this is predicted. And reserve the yellow dots that were happening. So we are out by that 2 year period. And I think that's the thing with this method, because these cycles are not precise. I mean, that's why sometimes we set cumulative column samples. Like, for example, the 11-year cycle can be a 10-year, or can be a 12-year cycle, 13-year cycle. Because they're not precise, we're going to be out in phase sometimes, but we're going to get the trends right. So anyways, what we're predicting is we're going to hang around at these lower than average water levels, the dash line is average. Not as low as the 2000s, maybe about, what is that? A couple feet above the summer 2000s, but still below average. And then after 2030, we'll down a little. But I would say, the thing to do with this method would be to update it every 5 years. And then I think you'd have a pretty good prediction 5 years out what's going to happen. And that's just the full 100 years warning that we're sitting right in. You're right now on just going to off down, drop it there. Okay. I'll leave these up here. I've sort of talked about them, and I need to be conclusions of being, but basically, the two top level conclusions are: be cautious in the environment, have to study what it means, and don't panic about it. But I think it's that we just have to be aware that climate is affecting these things as the lake levels. And that second conclusion is we have our method. Incidentally, I should have said this. It means on one of my slides. Our method doesn't include climate change. But if we update it every 5 or 10 years, the amount the climate's going to change over 5 or 10 years is probably small compared to the matched cyclical patterns on our Earth. And I think we have to recognize the cyclical patterns aren't going away. The sun The patterns of the sun and the El Nino and Nina, they're not going away. The ocean cycles and the growth of Atlantic Oscillation and La Nina, they could change. We don't really know yet, but the solar cycles aren't going to change. Anyway, that's my talk. Appreciate you listening and more further questions. We're